Morning all. I have a homemade problem that's very related to a recent SMO problem, the Singapore Math Olympiad problem, where you're supposed to count the number of uh, triangles that satisfy certain conditions. Okay, and combinatorics is just a big word for the mathematics of counting or enumeration. Now, right here, we're given the lengths of the sides of a triangle in terms of log base 3. The SMO problem produced by Wei Tan was base 10. So it's the same idea, it's just a different base, base 3 instead of base 10. Okay. Now, so you see we have constants here, log base 3 of 5, log base 3 of 16, and also we have a natural number n that can vary log base 3 of n. So we're supposed to find the number of possible values for n. Well, this just begs for using the triangle inequality, and also I'm assigning these values a, b, and c, so we don't have to keep writing these things down all the time. But these two statements down here are just a consequence of something called the triangle inequality. And it says unless it's a line or a degenerate triangle, the longest side is always going to be less than the sum of the other two sides. That's the triangle inequality, and that's just straightforward all the way back to middle school. If you have a triangle, the longest side is guaranteed to be smaller than the sum of the other two sides. Okay, so again, we're using the triangle inequality twice here. If C happened to be the longest leg of the triangle of interest, then its length would be less than the sum of the other two sides. And if B was the longest leg, its length would be less than the sum of the other two sides. Now, if you rearrange this, you get C kind of squeezed between B minus A and A plus B. And that gives us a way to set up an equation where we can actually count the number of triangles that would satisfy this condition. Now, what I did right here is just rewrite these guys. All of these can be written as like this would be 3 raised to the a. You don't necessarily even have to write this down, but 3 raised to the a is the exponential way to write this logarithmically. So 3 to the a is equal to 5. Okay, and then right here, and again, it's not really absolutely necessary to write this down. And then 3 raised to the b would be equal to 16. These are the exponential equivalents of the logarithmic statements. Okay. And again, I don't really think it's necessary to write that down. You can just use properties of logarithms, but just for the sake of clarity, I wrote them down anyway. Now, notice down here that we reached this final statement where we can do some counting based on the properties that if you have the log of the product, now this is any base, the log of the product of two values is equal to the sum of the logs, and that just follows from laws of exponents. So log of the product, this rings nice linguistically. The log of the product is the sum of the logs. Okay, so here we go, writing that down for you. The reason why I'm writing this down is it's probably unnecessary. I guess you guys probably all know this, but they're the two properties that you use to write down these two statements. Okay, like you can see right here, 5 times 16, we have a sum here. So the sum becomes a product. The sum becomes a product. And also for the difference or the quotient of two logarithms, the quotient of two logarithms, the log of the quotient is the difference of the numerator and the denominator. Okay, so we can write this as log, and it's any base, not just base 3. Log base x minus log base y. And I think it's crystal clear why I'm writing these down, because you see you have a minus condition right here, which corresponds to this minus. You see minus condition right here, minus condition, okay, and then a minus condition here. Then you have a sum condition right here, okay? So that's where these two statements come from, see? So we wrote it logarithmically, and now it gets very easy to count these, okay? Notice that 16 over 5 is not an integer, but it is greater than 3, right? 16 over 5 is not an integer, but it is greater than 3. So the next integer we could choose would be 4. Okay, 16 over 5 is just a little bit more than 3, right? Okay, and so our possible integers, we're looking for integers, positive integers, natural numbers. The first one would be n equals 4. Okay. Logarithm's an increasing function. You could have 4 or 5. And we'll go ahead and put the infamous ellipsis ... Now 5 times 16 is 80. We have to be strictly less than 80, so it would be 4 through, we can go 78, 79, like that. Okay. Now we're supposed to count the number of n's. So we have the numbers. We've enumerated them. We've listed them. How many of them are there? Well, you start at 4 and you end at 79. It's tempting to say that would be 76, but that's actually 70. It's tempting to say that would be 75, but it's actually 76, right? Like the numbers 4 and 5 are two numbers, but 5 minus 4 is 1, right? So that sometimes confuses people. So there's 76 possibilities, ladies and gentlemen, 76 triangles that would meet these constraints. Okay, and again, what I did is I just did 79 minus 4, and then I added 1, right? Because it's just a counting principle, right? 79 minus 4 plus 1 would be the actual count, the actual number of values of n. Now, just a little bit of, maybe, I don't know if this is worth the time, but I'll go ahead and do it. You could actually draw a triangle like if n was equal to, let's say, 9. Okay? If n was equal to 9, we actually would get a triangle that looks something like this, and I'll try to scale it. Log base 3 of 9 is 2, right? Okay, so we would have a triangle that maybe looked, let me draw it, do the best I can here. So there's we'll call that length 2, right? Okay, now notice that log base 3 of 16 over 5 is just a number a little bit bigger than 1, right? Because log base 3 of 3 would be 1, right? And so we would have another triangle here, maybe, and I'm trying to scale this part of the triangle. I'm not trying to necessarily say this is a right triangle. This would be the triangle. This would be the length log base 3 of 16 over 5. Log base 3 of 16 over 5. And again, I'm intentionally trying to make it a smaller looking number than 2 because, again, 16 over 5 is 3. Log base 16 over 5 is close to 3, right? Okay. Whoops, sorry, folks. That's 16 over 5. Now, this next number is quite a bit bigger. Log base 3 of 80 would be almost, let's see, 4, right? Because 3 to the 4th is 81. So the triangle that we're talking about here, let's see, did I manage to do this? Well, yeah, I didn't do so good with this. Let's maybe make a more accurate picture would be something like this, maybe like this. We'll go ahead and do 2 like this, and then we'll do log base 3 like that, right? And so this is more realistic. That would be a more realistic triangle, maybe. It really, but I think you get the point. I made this one too long, actually. But in any event, there's 76. There's 76, and that was the problem. We counted up 76 total triangles that satisfies the condition. Hope you enjoy.